I hope you're doing well. So essentially, I decided na online lang muna dahil alam naman natin na medyo mapapagod, napagod tayo sa exam natin last night. Although yung other sections, I believe yung 8 to 10 na class ay nag-online na class din, pero yung 9 to 11 class ay nag-face-to-face meeting. Pero tayo, marami tayong hahabulin because ang i-discuss natin is essentially design ng beams at saka ng columns. So anything that involves beams and involving columns, yun yung itatakal natin because yun yung magiging coverage sa third exam that is scheduled on November 20, if my memory serves me right. So essentially after this week, we have additional 2 weeks to discuss how are we designing yung beams and how are we designing yung columns. And expect nyo rin na around this week din, marirelease yung project na part 3 na specifications on which you design those beams, and you design those columns. So mahalaga itong magiging lecture natin on guiding you on how to do that specific part of the project. And as a bit of reminder, remember na yung part 1, so yung MSA na part is scheduled on November 8 and yung part 2 is scheduled to be submitted at least yung deadline on or before November 15. So reminder lang ulit. So now after dealing with trust members, we deal with syempre ang conditions nga natin for trust members is dapat walang shear and walang moment. Because pag nagkaroon ng shear and kapag nagkaroon ng moment, we have to proceed into what's called flexure design. So flexure essentially involves shear at saka bending moment. Ang question na lang is whether those members are or whether the design that you're making or the sections that you're assigning to your beams and columns eventually are adequate enough to sustain yung mga design loads natin. So, syempre, if we recall from ES102, sa ES102 is ES102 somehow gives you a glimpse on how to compute yung bending stresses using yung using this formula right here. So yung sigma is equals to my over I, on which yung y is yung distance ng farthest fiber. And yung yung I is yung moment of inertia at the neutral axis. But as we have tackled, in particular sa compression design and particularly dun sa exam, we have to be wary of the strong axis and the weak axis. So at most times, syempre, ang dinideal with natin na moment of inertia is yung moment of inertia along its strong axis, which is this Ix right here. Pero there is also this weak axis, which is called Iy. And down the line, siguro kapag nasa industry na tayo, when we deal with we also deal with angled sections, hindi na lang siya simpleng Ix, hindi na lang din siya simple na Iy because we need to identify yung tinatawag na weak axis. Yung pinaka-weak na axis which is yung pina-quote natin as Iz, which yung pinagmulan ng Rz. Pero yun, i-retain nyo lang yung thought na yun. So that is for compression design. Oops, teka lang, meron tayong i-admit sa meeting. Okay, mabalik tayo dito. So, once we deal with angle, remember na hindi na mag-apply itong formula na to, yung formula given from ES102. So, from your CE18, which is supposed to be taken simultaneously with CE151, meron tayong unsymmetric bending na formula. So, meron kang ganito, then meron kang ganito. So, lahat ito ay magre-reflect eventually dun sa code provisions, particularly dun sa angle na member. So, all of these magagamit natin, although magfo-focus tayo in particular kasi ang ninonominate naman natin kadalasan as beams ay yung mga symmetric na section. And kapag in-apply natin yung symmetric na section, mauuwi tayo on this or rather, mauuwi tayo on the biaxial bending formula. So kung lalagay ko na mz y over iz, this is negative, plus my z over I y. So this will be your biaxial bending formula. So why in the first place kinukuha natin yung sigma or yung stress? Because ito yung magiging ultimate limit state natin. Supposedly, we want to determine whether yung beam mo is capable of handling all of the external forces. And one of the indicators is whether itong stress na to exceeds yung kadalasan to. Pag yan exceed, supposedly na na-exceed na niya yung yielding and the beam actually experiences non-linear action. So ito supposedly yung yielding limit. So sorry, dapat less than to. Yielding limit. Pero theoretically, we can still proceed or if draw natin yung cross-section right here and i-draw natin yung shear stress diagram. So yung yielding limit states that if itong beam na to is subjected, itong cross-section na to is subjected to what's called the yielding stress, yielding moment rather, yung magiging maximum na bending stress is supposedly yung yielding stress. So sigma y or syempre, since nasa CE151 tayo, medyo ibahin lang natin siya ng konti because ang terminologies natin for CE151 is yung capital letter F as your stress right here. P is yung force. So again, reminder lang ulit sa ating lahat. So meron kang ganitong set of functions. So supposedly, ito yung parang from your ES102 na ito yung parang kaya. So, pero in reality, meron pang theoretical maximum ito. We wanted to fully optimize yung capacity nitong beam na to. Hence, we consider yung theoretical maximum such that meron ka lahat ng fibers mo are under yielding. So ito yung ultimately na makakayatan niya na state of stresses. And this would result in into a bending moment that is termed as the plastic moment right here. So sa code, kadalasan meron tayong tinatawag na section modulus. And meron tayong tinatawag na plastic modulus. So sa section modulus, this will able us to solve for ano bang tamang sige. So supposedly sa code, hindi natin concern yung yielding moment. But rather meron tayo later na tatawagin na residual moment, MRX and MRY. So, itong section modulus na to is S sub X and S sub Y. So, ito yung kailangan natin to get yung residual moment along X and residual moment along Y. Hold on to that thought kung ano yung residual moment because magagamit natin siya later on. At the same time, meron ka rin tinatawag na plastic modulus. So, ito yung MP and pwede ito along x-axis, along its strong axis, bending along its strong axis, or plastic yielding due to the bending moment applied along the y-axis. So meron kang z sub x and meron kang z sub y. So yung s sub x is essentially, if we know na this is along the strong axis, s sub x is essentially ix over y max. O nga pala, nag-i-interchange, no? Biglang from z-axis, naging x-axis. So, ano lang natin, set lang natin na this time, unlike sa terminologies from above, from your ES 102, on which yung x is yung axial, yung y is yung strong axis, then yung z yung ating weak axis. This time, if we browse through the codes, yung x is actually yung strong axis, yung y is yung weak axis. So, dito, ilagay na natin na at this point, CE151 and yung code AISC na terminologies yung ating ginagamit. So, yung S sub X is essentially yung IX. So, yung I, nakukuha mo along the strong axis right here. So, ito yung strong axis mo. Then, yung Y max mo is yung distance ng farthest fiber right here. Ganon din naman sa weak axis. Otherwise, mayroon kang IY, so yung moment of inertia along your weak axis. Then, meron kang distance ng farthest fiber. So, meron kang, this is yung Y. So, never mind na lang yung nailagay. So, kung babalikan nyo itong ibibigay na PDF na notes, take note nyo lang na parang on the gis lang siya nilagay. And hindi na siya magiging related dun sa bending stress diagram na nakalagay dito. Tapos ito yung x max natin. Sorry. Iyan yung s sub x at saka x s sub y. Tapos yung plastic modulus is rather taken in this manner na z sub x, kung ano man yung makompute mo na plastic moment, MPX divided by yung yielding stress right here. Pero actually, there's another way to deal with this. Pwede mong sabihin na if ito only on the condition na if doubly symmetrical yung section mo, this can be equal to 2 times QX ng top. Sorry. Burahin ko lang. Hindi yung dapat subscript yan. Top. What do we mean by Q sub X? Itong part na ito. So, kung ito yung neutral axis, which is also the centroidal axis and the plastic neutral axis, so yung kahit yung nasa taas lang na first moment of area, then minultiply mo by 2, yun yung z sub x. If and only if doubly symmetrical yung section mo. So, in such way na hindi na uusog yung neutral axis mo. Hindi mo na siya kailangan hanapin. So, if doubly symmetrical, this will apply. Same goes with ZY, which is MPY over FY. So, ganun lang din. Since doubly symmetrical, this, siguro kahit lagay lang natin na left, this can also apply. Na ito lang yung kukunan natin ng, so yung highlighted in black, yun yung kukunan natin ng first moment of area, i-multiply mo by 2, meron ka ng z sub y. Pero no need to sweat about this because ito ay makikita natin kay table 1-1 for wide flange section. So available naman siya. Unless meron kang, so kaya ko lang din sinasabi sa inyo, yung theoretical nito, netong part na to, is if binigyan ka ng built-up na section on which hindi na available sa mga tables yung section properties. So you need to derive those section properties yourself. So here are the formula for your convenience. So what I've been mentioning so far is yung theoretical maximum nga. If we say yung theoretical maximum, what I'm pertaining to is yung plastic moment. Or kung sasabihin natin na limit state, anong mode of failure? Ito, plastic yielding. So, siguro briefly kong i-mention na if nangyari yung plastic yielding, nagkakaroon ng, so kung nasa field ka na or nasa design, maririnig mo to palagi, yung formation ng tinatawag na plastic hinges. So halimbawa, meron kang uniformly distributed load right here, meron kang ganyan, na magkukos ng yielding, ng plastic yielding. Pag na-reach niya yung plastic yielding na yan, ang mangyayari is that magkakaroon ka ng hinge dito. And kapag nagkaroon ng hinge dyan, magiging unstable na itong beam na ito. Because it's allowed to move na along this axis. So, ang mangyayari lang is magdidip na siya ng paganyan. Ito na yung magiging deformed state mo. It will be unable to carry yung loads. Kaya ito yung theoretical maximum. Ito yung dinedetermine natin na ultimate limit. Pero most of the times, hindi tayo umaabot dito sa plastic yielding. And mabalikan lang natin, if ilalagay natin to sa code provisions, meron kang tinatawag na nominal na moment. If we say na plastic yielding, yung limit state natin, so meron kang M and X, so yung nominal moment mo for bending about X is equals to Fy Z sub X. And take note na for this limit state, yung under strength factor is equals to 0.9. So ganito rin yung sa bending along Y. So meron kang Fy Z Y. So meron kang Z sub X, meron kang Z sub Y, which you can get at table 3-1. Then, for example, meron kang mga certain examples on which, considering this, ano yung kaya ng beam. So those are the types of problems. So ano yung mga conditions para masabi natin na plastic yielding yung mag-govern? So this will govern if, one, the cross-section, the section selected is compact. So compact, so kailangan na naman nating i-check yung width to thickness ratio ng flange, yung width to thickness ratio ulit ng web. So supposedly these are yung width to thickness ratio are less than dun sa limiting width to thickness ratio. And take note, unlike nung sa katulad nung sa compression, pero ibang table yung titingnan mo for 0.1B, 4-1B. Rather yung hahanapin na natin. Later on, check natin. Second is that the section is laterally braced throughout. So, any conditions na magkukos ng instability dapat ay absent for us to be certain na plastic yielding yung mag-govern. So para ito yung magiging, so kung i-compare natin, so dapat to say na tama yung design natin, meron kang, so burahin ko lang. So meron kang Fy M, ba't may M? Fy Z X. Kadalasan, ganyan tong plastic yielding. Mag-a-admit lang ulit sa room. Admit tayo. So ito yung conditions. Kasi otherwise, we need to consider the other limit states. So we browse through the AISC provision. So kung gusto mong malaman how to design, basically chapter F got all of that covered for you. But we'll be browsing some of the general provisions and we discuss a little bit about the limit states. So kapag yung cross-section mo is particularly na so nagtatanong na palagi doon sa cross-section mo whether slender yung flange or whether slender yung web. So apart from the cross-sections that we're dealing with. Tapos sinasabi rin, saan mo hahanapin sa chapter F? So merong mga subsections yan hanggang F12. So ito yung mga conditions, mga limit states that we need to look out for, specific conditions. So what are these pertaining to? So dun sa unang row, this one right here, F2 pertains to conditions such that ito. ito essentially, itong dalawang conditions na to. Yung section is compact. Both the web and the flange are compact. Pero there are also specific provisions. The code will direct you to subsection F3 if, for example, si flange mo is non-compact na. While at the same time, kung slender na siya. So parang meron kang compact, non-compact, and slender. Unlike nung sa columns na meron ka lang compact, ay slender at saka non-slender na cross-section or slender or non-slender na length. Diba? Na overall length. Dito, meron ka ng compact, non-compact, at saka slender. Pag sinabi mong compact, so i-highlight ko na, pag sinabi nating compact dito, essentially plastic yielding will govern. Pag sinabi mong non-compact, meron kang inelastic buckling. And kapag sinabi mo na slender, elastic buckling. So how do we distinguish yung inelastic buckling dun sa elastic buckling? Mabalikan natin yung hinold on natin na to, itong MRX at saka yung MRY. So kung babalikan natin halimbawa yung parang quote-unquote actual na shear strain diagram. So this is yung strain, this is yung stress ng section mo. Once na na-reach niya yung certain amount ng stress on which kung in-add up mo with the residual stress, diba? Pag hinatroll natin, meron kang residual stress. So kung ipuput on top mo siya with the applied stress, pwedeng pag nag-add up yung dalawa, mag-exceed siya ng yielding stress. So magkakaroon ka ng non-linear action at that point. So, di ba, ang tinatanong na lang, during this non-linear action, ano yung i-consider natin? So to recap ulit, ano yung i-consider natin? Remember na instead na this is yung E, ang kino-consider mo na modulus of elasticity is yung tangent modulus. So essentially, this is where yung etong part na to is where you identify yung tinatawag na residual moment. So yung residual moment is sinasabi lang niya na hindi na siya aabot dito. Hindi na siya aabot dito. Mapapaaga yung onset. Paano mapapaaga yung onset? Like if nag-compute tayo ng my na equal to my over I, hindi na yielding to, yielding. Hindi siya yung moment along y. Hindi na siya aabot dito. Rather, meron kang MR right here, tapos meron kang mali pala yung Stress pala to, stress. Yielding stress. Meron ka ng 0.7 F sub y S sub x. Mabalikan natin yung formula ng S sub x natin. So parang naglagay ka ng 0.7. So as observed kasi sa site, due to the residual stresses, once na 70% na ng yielding stress, yung na-experience na bending stresses ng section mo, doon napapaaga yung onset. And dito sa part na to, nangyayari yung inelastic buckling. Then, dito sa part naman na to, dito nangyayari yung elastic buckling. So, ibig sabihin, hindi pa siya nagre-reach ng, wala pang inelastic action, kahit na nasa elastic region pa, nagkaroon na ng buckling, whether sa buong section or doon sa flange or sa web mo, nagkakaroon na ng instability, unable na yung beam mo, and in extension later on, yung column mo, na i-handle yung forces. Tapos nandito yung plastic yielding. Pero later on, mapapansin nyo na baliktad yung presentation. So, we are identifying what's called the residual moment. So, yung residual moment along X is this formula right here. 70% of that of the yielding stress. Then, meron ka ring residual moment along Y. Pero kadalasan, take note, ito yung madalas na na-highlight. Because what we'll realize later on is this part right here is only applies kung local yung buckling. Nagkakaroon ka ng buckling along flange. So, anong itsura ng buckling along flange? Meron kang cross-section, tapos yung flange mo ay nag-buckle ng ganyan. So, sample lang naman. So, yun yung buckling dun sa flange. So, mabalik tayo dito. So, kaya tinatanong whether compact or non-compact or slender yung ating flange. Tapos, for web slenderness, ang consider lang is kung compact and non-compact kasi medyo magiging particular tayo kung kahit na yung web mo ay slender na. Medyo magiging maarte na tayo. Tapos, what are these yielding limit states na nami-mention? So, meron kang Y, this stands for plastic yielding. Tapos, LTB stands for lateral torsional buckling. Didiscuss natin to pa isa-isa. Yung FLB is flange local buckling. Yung other, hindi ko na ganong, parang, hindi ko na rin ganong i-discuss. So, torsional flange back yielding, yun yung PFY. Tapos, ano pa bang meron? Compression flange yielding, yun naman yung CFY. So, yun yung nangyayari dito. So, those are the limit states that we have to consider. So, nakalista na siya sa ito yung second page ng chapter F. Dito mo siya makikita. So as for the general provisions, again, most of the time, or all of the time, rather, if we were considering buckling, we take na yung under strength factor for flexure is always 0.9. Tapos, babalikan natin to later on, yung lateral torsioning modification factor. Ang kadalasan kasing dinidiscuss una is this limit states right here. Itong F, L, D, yung flange local buckling. Kasi we need to check first yung flange slenderness at saka yung web slenderness. We need to identify whether meron kang compact, non-compact, and slender. So, paano natin ma-determine? So, again, sa flange, meron kang width to thickness ratio ng flange. So, inano lang natin, lambda F is equals to width ng flange divided by 2 times the thickness ng flange. So ito yung kailangan nating i-compare in the first place. So actually, misplace siya. Burahin ko na muna rin to. Kasi ilagay lang muna natin na yung flange ay width ng flange tapos divided by 2 times thickness. Ganon din yung sa web na meron kang H over TW. Both of these ay makikita mo kay table 1 for wide flange section. So ito makikita mo kay table 1-1. Tapos ang kailangan na nga nating i-check is whether compact, non-compact, or slender yung ating cross section. So again, pag compact, plastic yielding yung mag-govern dito. Pag non-compact, inelastic, flange local buckling. Pag slender, elastic, flange local buckling. So, saan natin makukuha itong mga formula na to? So, we need to look for table 4.1b. So, yung 4.1a ay kay columns. Yung 4.1b ay kay beams. So, ito yung particularly nating titignan. Pero, wait. Supposedly, case 15 na kasi to. Case 10 yung una nating titignan. So, merong difference yung built up dun sa hot rolled. So, yung hot rolled ay falls under case 10. So, sa case 10, for compact, to say na compact or non-compact, dalawa yung titingnan natin. Meron kang delta, lambda P, saka lambda R. So, pag sinabi natin na compact, essentially, pag sinabi mong compact yung flange mo, dapat less than siya sa lambda P. So, we need to identify yung lambda P. So, if we take yung table 3-2 for hot rolled section, yung lambda P ay equal to 0.38 E over F sub Y. So, this is very particular. This is case 10. Tandaan natin. Case 10 ito. Case 11, mag-iiba ng konti. Tapos, meron kang non-compact na section. So, ang mangyayari kapag non-compact na section, somehow, yung width to thickness ratio ng flange mo is greater than that o the limiting width to thickness ratio for compact sections, but it is still less than the limiting width to thickness ratio ng slender na cross section. So yung delta R mo rito ay equal to, so if we take also yung case 10, E over F Y. So ito yung case 10 left. So kapag nag-fall between the two, yung width to thickness ratio mo, it falls under non-compact. And actually, ito yung interesting na, parang interesting out of the two, out of the three rather na, na cross-section. Pag slender, ito, ang na-determine mo is si flange mo ay greater than dun sa lambda R mo. So magiging elastic buckling na siya. And if we browse through section 2, actually ang makikita mo rito, so nauna kasi palaging dinidiscuss yung yung LTB before yung FLB. Pero sa book, palaging nauuna yung FLB before dinidiscuss yung LTB. So, balikan natin. So, if na-establish natin na compact, ulitin natin, yung magiging MN mo ay equal lang kay F sub Y, C sub X. If slender, unahin muna natin to, yung MN mo is equals to E KZ S sub X. Nakalimutan ko na yung formula. So may 0.9 plus lambda square. 0.9 tapos lambda squared. So whatever was the width to thickness ratio nito, yun yung magiging bending moment ng yung nominal moment natin for slender na cross section. Pero most of the time, hindi tayo nagde-design ng slender na beam in the first place. Typically, at most, inaalaw natin na non-compact yung cross section. So yung non-compact na cross section, balikan natin ito. This is actually yung non-compact na section. This is yung compact na cross-section. This is yung slender na cross-section. So essentially, what we're trying to do with non-compact section, and based on experimental results naman, na allowable na i-interpolate mo between, so yung value nito, yung mn, is somehow in between MR at saka MP. Ganun palagi siya. Ang tanong na lang, paano mo makukuha specifically yung value? We simply have to interpolate. So meron kang MP, so whether X or Y axis o along the strong or weak axis, pero lagay lang muna natin na MP, na i-benchmark lang natin siya. Tapos meron kang MP minus MR over lambda R minus lambda P times lambda F times lambda minus lambda P. Lambda P. So ito yung interpolation na nangyayari between the two. So if we were to track, halimbawa, yung lambda right here, tapos ikukumpara natin siya with MN. So kung compact yung cross-section, so halimbawa this is lambda P, tapos halimbawa this is lambda R, yung behavior niya is ceiling lang siya. Ito yung MP natin. Tapos sa lambda R, at the exact moment na umabot ka sa lambda R, ang makukuha mo actually dito is si M sub R. Tapos at that point, further on, medyo magiging ganito yung behavior niya pag elastic buckling. Between those two, what this formula is pertaining to is mag-interpolate ka lang between those two. So ito yung behavior ng flanges mo. Ay ng beam mo. Remember na dalawa yung kailangan nating tignan. So whether yung flange mo is compact or non-compact and slender, or yung web mo is compact or non-compact and slender. So kung i-check mo, meron kang case 10. This is for hot roll section. Take note natin na meron tayong case 11. So palaging lalabas si ating friend na KC na square root of H over TW. And dapat hindi siya greater than, it has to be less than 0.76 for all calculation purposes and not less than 0.35. So kapag bumaba siya ng 0.35, 0.35 na gagamitin mo. Kung lumagpas siya ng 0.76, 0.76 yung gagamitin mo for KC. So ito, dito mo siya gagamitin. But there are times na nape-prevent yung buckling ng flange. How is the buckling on flange actually prevented in the first place? So halimbawa, meron kang wide flange section dito. Tapos sabi ng engineer or okay, built up, for example, itong na-built up na cross-section ko ay pala, slender or non-compact. Anong gagawin ko? Naglalagay sila ng tinatawag na stiffeners dito. So, kasi kung ngingiti yung, so kung positive yung moment, take note kung positive yung moment, ang mangyayari is this one is under compression, this is under tension. And nangyayari lang yung buckling kapag yung part na yun ng beam, ng cross-section mo is undergoing compression. So dito, maglalagay. Pero wala itong silbi, mangyayari yung flange local buckling if negative yung moment tapos nandito sa top flange mo ilagay. So pag negative yung moment kasi, yung magiging magiging bending stresses mo is ito na yung under tension, ito yung under compression. Kahit na maglagay ka dito, FLB will still occur. Dito mangyayari yung flange local buckling. Dito. Pero say, umabot tayo dun sa case. Okay, granted na meron ka ng stiffener dun sa flange mo. Parang lateral, parang pwede mo na masabi na laterally supported yung top flange mo throughout. Granted that it experiences positive movement. So, ganyan. Granted na ganyan. Then, yung next mong i-look out for is whether yung web mo can experience web local buckling. So, sa web local buckling, what we need to look out for is yung limiting width to thickness ratio ng web mo. And kapag umabot dun sa point na yon, ito yung gagamitin natin. F3 pa rin. Steel section F3. F5 na pala ang gagamitin natin. So, merong specific na formulas. So, ano muna? Any questions ba so far? Sige, sa chat, tingnan natin. Yung MY yung pinakita ko kanina. So, questions? Malinaw ba yung raise lang ng hand? Okay naman tayo? Sige. That is the analysis and eventually design involving laterally supported na beams. Pero we have to take note na hindi all the times na laterally supported yan. Na walang stiffeners or minsan walang bracing. So, ang nangyayari kasi when you subject, siguro later, or rather i-check niyo na lang yung study guide. Iniiwasan ko na lang i-discuss din yung na to. Yung theory nito is if for example sinubject mo nga siya under bending moment, there is this tendency as observed with halimbawa nag-apply ka ng for hindi naman symmetrical ngayon, so singly symmetrical lang, halimbawa channel section, nag-apply ka ng load, and dahil yung load na yon ay hindi nasa shear center, ang nangyayari dito is nagkakaroon ng unnecessary na rotation, and eventually yung magiging deformed state niya ay magiging ganito. Actually, nangyari din siya kahit na doubly symmetrical yung cross-section mo. And ito ay nangyayari, it's mainly because of what's called warping. Kapag nagkaroon ka ng warping, eventually, ganito yung magiging itsura ng cross-section mo. Pwedeng mag-warp yung compression flange mo in particular. So, what happens here is, if iti-check natin, halimbawa yung original na state, so i-draw lang natin yung beam. Burahin na lang natin. Try ko mag-draw muna ng straight line. Draw muna ng straight line para malinaw. Yeah, straight line. Then, straight line. Then, ito gagawin ko na lang dash. So, meron kang ganyan. So, halimbawa, yan. Kung titignan natin ng top view, dahil dito sa warping na to, yung magiging deform shape niya ay magiging ganito. Ikakaroon ka ng sideways na motion. And kapag nagkaroon ng gantong sideways na motion, this beam can no longer handle any uh, any flexure pa. Hindi na siya magko-contribute whatsoever sa flexure. Magiging unstable na to beam na to. And this is what's called lateral. Kaya may lateral, tapos meron ding torsional. Lateral torsional buckling. Torsional, it's mainly because nagkaroon ng twisting dito. Ito yung twisting na nangyari. Lateral, ibig sabihin nagkaroon ka ng lateral motion dito. So ito ay nangyayari maski nasa centroid pa. So kahit nasa shear center pa, naka-apply yung load. So meron kang gantong uri ng stability. And katulad ngayon ng sa column, dahil parang isipin nyo na ito yung magiging deform shape. So sa column merong ganyan, tapos yung deform shape ay ganito. Magiging concern na natin yung bracing. So hindi mangyayari to dun sa unang part. If laterally braced throughout, pine-prevent mo tong lateral motion na to. Ito yung pine-prevent mo in the first place. Kaya mahalaga yung condition. We need to check kung meron kang lateral support throughout, kung mangyayari itong lateral torsional buckling. So, mahalaga ngayon yung lateral support. Saan ngayon nangyaring yung bracing? So, balikan natin. If merong bracing halimbawa dito, saka dito, at saka dito, yung mai-imagine mo na deform shape for the beam, if you check sa upward, ay magiging ganito. And alam natin na dahil umikli yung length, katulad nung sa column natin, dahil umikli yung length, this will require a greater amount ng force kumpara kung at the ends lang halimbawa na brace siya, na pinaprevent mo yung displacement. So this parang kung meron kang M na makukuha rito, mas meron kang MN na makukuha dito, definitely, para mangyari itong nasa right, kailangan mo ng mas malakas na bending moment kumpara dun sa nasa left. This is where the general provisions of the AISC is really starting to discuss on. Parang ito yung starting point ng discussion sa AISC. We need to consider first daw, kasi most of the times, kasi special provision lang naman, kadalasan na if laterally supported throughout, we can write off yung lateral torsional buckling and we consider other limit states. Pero take note, pwedeng mangyari pareho yung flange local buckling at saka yung lateral torsional buckling. Pwedeng mangyari siya in such way na yes, kahit na walang lateral support throughout, then madedetermine mo na dahil slender halimbawa yung mga yung cross section mo, pwedeng mauna si flange local buckling kaysa kay lateral torsional buckling. Such instances can happen. So how do we compute for the lateral torsional buckling? So we hold on to the thought muna ng C sub B for a while, because this will require us to draw our bending moment diagram. So meron kang M-max, meron kang M-max, meron kang MA, meron kang MB, meron kang MC. What are these three pertaining to? So if we were to draw our bending moment diagram, halimbawa meron kang yung typical. So sige, point node at the midspan. So we'll have this, isin lang natin, we'll have this bending moment. And we know that ito yung M, and at the same time, ito din yung M max. Ito yung maximum na moment. So yun yung ipa-plug in natin dito. At while at the same time, meron kang, if yung conditions na yung bracing is only provided at the ends or at the supports, right there, what we would consider is meron kang MA. MA is 1/4 the distance ng unbraced length. So ito, this will give you MA. MB is 1/2 the distance. So kung ano man yung bending moment doon. MC is 3/4 the distance. Tapos on top of that, meron kang M max right there. Pero halimbawa, okay lang natin, then i-paste natin dito. Halimbawa, this time, hirap lang nag-auto tigil yung ano. This time, ang nangyari is meron ka na ring lateral brace dito. May ano ka na, lateral bracing diyan. Dinidisallow mo na yung movement diyan. Ito at saka ito na yung i-consider mo na tinatawag na unbraced length. And kadalasan or all of the time pala, ang ginagawa na natin is yung MA mo ngayon is 1/4 of that. So ito na yung bago mong MA. Yung bago mo ng MB is 1/2 ng unbraced length. So kung consider mo sa overall length, medyo mga lahati na siya. MB, tapos meron ka ng MC dito. Tapos meron ka pang MX. So nandun pa rin naman siya sa span na yun. So ito yung kailangan mo na formula. And kadalasan, meron ding somehow shortcut assistance na ino-offer sa'yo sa AISC. Pwede mo itong makita kay table 3-1. So makikita mo to kay table 3-1 over very specific na loadings. Then mamaya, tatanungin natin, sir, paano ba kunin yung bending moment diagram? Kasi kailangan natin pala sa CSAB yan. The AISC also get you covered. But we proceed on discussing muna some of the topics. So, kung kino-consider natin yung lateral torsional buckling, similar halos siya kay flange local buckling. The only difference, kung mapapansin mo, is yung presence nitong C sub B as your multiplier dito. So, ito ay katulad lang nung sa ano. So, you're interpolating between MP saka MR. Ganun lang yung nangyayari dito. Tapos, ang ginagamit pang interpolate is yung unbraced length. So, unlike nung last time na yung width to thickness ratio ng flange, meron kang unbraced length dyan. Tapos, meron kang pang-define na anong length yung anong length yung kailangan para maging slender yung beam mo on which mangyayaring elastic lateral torsional buckling. Tapos meron kang LP. Ito yung length, unbraced length ng beam mo on which if the beam's unbraced length is less than L sub P, then ang mangyayari is yielding. So plastic yielding yung mag-govern. So you're interpolating between those two values. And if greater than dun sa sa slender na limit ng length, yung unbraced length mo, kailangan mo na mag-identify ng tinatawag na F critical. At itong F critical, makikita mo dito. Lahat ito ay available dun sa table. So, ulit, yung C sub B na kinocompute natin dito, tapos meron kang pi squared. So parang similar lang dun sa sa compression kasi nga ganun yung nangyayari. So meron kang pi squared E which we know to be 29,000 KSI if we're talking about English units. Meron kang unbraced length LB right here. Yung RTS makikita mo to kay table 1-1. Si J makikita mo kay table 1-1. Si C, makikita mo kay table 1-1. Si S sub X, si section modulus, makikita mo kay table 1-1. Si H sub O, makikita mo rin kay table 1-1. But somehow, pwede mo rin actually siyang isolve on your own given yung layout ng cross-section mo. Kasi if for example na built up na cross-section siya, there's a need for us to solve for RTS, for S sub X, for H sub O, for J, for C, for L, RTS din dito. Ito ay actually nanggaling dun sa sumunod lang. Ito ay nanggaling actually sa ito yung classical solution dun sa ODE that details yung effect ng lateral torsional buckling. So, yung L sub P, so medyo mahaba-haba din to. Yung L sub P is computed in this manner na meron kang 0.76 ay 1.76. So, teka, epal yung selection ng text. 1.76. Tapos yung R sub Y na pwede mong makita sa table 1-1. Kasi ito yung sa weak axis na radius of gyration. Tapos meron kang E. So, tapos yung Fy. So, depende kung anong strength. Yun yung L sub P natin. So, kunin mo yung square root nun. And you have the computations for L sub P. Take note Take note pala. Ang R sub Y na nilagay mo rito ay in inches. So kapag kinompute mo using this, ang lalabas is a value in inches. Iko-convert mo pa siya into feet. And then divide mo by 12. Tapos ito medyo mahaba-haba, yung L sub R. So yung L sub R, kailangan natin ito. So highlight natin 1.95 RTS. Ito ay makikita mo kay table 1-1. E, we know to be equal to 29,000. 0.7 Fy, essentially ito yung residual na stress mo. Yung J is yung polar moment of inertia. Yung C, makikita mo rin kay table 1-1. S sub X, section modulus. H sub O kay table 1-1 din. Tapos J, ulit ito. C ito. S sub X, H sub O. Tapos meron kang some constant right here, pero may pinanggalingan din to. Ito yung 29,000 over, parang square root of 29,000 over some value. Tapos meron kang 0.7, F sub Y. Tapos meron kang E, then is-square mo ito. So yan yung formula for L sub R. Tapos take note, kung halimbawa ang built-up section, hindi ka naman niya iiwanan na hanging in the air. So, meron kang RTS, formula for RTS squared. So, you simply have to take the square root of this term para makuha yung RTS na kailangan natin dito. At the same time, yung coefficient ng C is always equal to 1 kung doubly symmetric na I-shape. Kung channel, kailangan mo siyang i-compute. Tapos, this can be approximated using this. And ang na-miss ko ata dito, ito yung solution actually, galing dun sa ODE na formulation ng lateral torsional buckling. Ito yung actual na solution. Yan yung pi E squared over LB. Yun, doon mag-appear yung sige, nakalimutan. Yung C sub W, hanapin lang natin. Wala pala sa code yung formula ng C sub W. Yung C sub W is what's called the warping factor. Ito, makikita mo kay table 1-1. Pero, if we want to get yung C sub W, I believe ang kailangan mong kunin is yung moment of inertia ng top flange. Ganun mo makukuha si C sub W from that information mo siya matederive. Pero this is also available in table 1-1 for hot rolled section. Kung Kung hot rod. Kung built up, kailangan mo tong solve. So sa lista na lang yung magbibigay sa inyo ng built up na section. So, yun. That concludes actually yung F2 and yung F3. So, we proceed with discussing ano ba yung mga tables na makakatulong sa atin when dealing with design. Kasi, halimbawa, kung magde-design ka, kailangan ko ba maghanap ng ng parang limiting width to thickness ratio ba? Tapos at the same time, kailangan ko bang kailangan ko ba i-limit yung unbraced length? Ililimit kasi alimbawa tatlong limit state to. Yielding, inelastic lateral torsional buckling, elastic lateral torsional buckling. Saan ko specifically i-place yung mga column ko? Paano ko makapagbigay ng first na intelligent guess? Hence the reason why bukod dito sa table 1-1 to assist you, meron ding sets ng table na ino-offer dun sa mga table trees yung pino-provide sa inyo for assistance. So to recall, ito yung difference between compact, non-compact, and slender na cross-section. Kasi ito yung ginagawa ni C sub B. So si C sub B, kadalasan, take note si C sub B is always greater than 1. Never siya magiging less than 1. If nakakuha ka ng C sub B na less than 1, mali yung C sub B na compute mo. Ang implications kasi ni C sub B is meron ka nito. So, mag-provide lang ako ng explainer dun sa sa values. So, originally, ito yung ito talaga yung kung C sub B is equals to 1, so kung uniform na moment lang siya, C sub B is equals to 1. Ngayon, kung C sub B is greater than 1, actually, yung magiging formula mo, para ka nag-multiply ng C sub B all throughout. So, parang magkakaroon ng offset ng ganito. Ayusin ko lang. Delete. C sub B na ganito. Pero take note na na-compute mo, lateral torsional buckling na capacity na C sub B, tapos sabi, greater than dun sa M sub P. Hindi pwedeng mangyari yun. Ito talaga yung upper limit. Kaya ililimit, kahit na-compute mo na C sub B, M sub N na greater than M sub P, kailangan mo pa rin na ibalik siya kay M sub P. Ito pa rin yung magiging envelope mo ng capacities. So, ganun siya. Ganun yung ginagawa ni C sub P. Nini-increase lang niya by some factor yung moment capacity, but it should be always less than still by 2 M sub P, or else M sub P yung SSF natin. So take note, ito ulit yung mga formula, mga pertinent formula, ganun din for non-compact flanges, ganun pa rin yung formula natin. Then, meron kang, ito yung, sige, nung panahon namin, ASC version 14, wala pa yung tinatawag na table 6-2. Pero ito ay very particular na, and i-discuss natin on the design involving columns. Kasi table 6 pertains to combined axial and bending. So table 6 is combined axial and bending. And si 6-2 in particular is meron kang KL na pwedeng i-treat din as L sub B. Kapag sa bawat section, meron kang P sub N, tapos meron ka rin M sub N na pwedeng i-look out for. Ito yung in-offer ni table 6-2. Kaya sinasabi sa code na pwede mong simulan using table 6-2. Pero that's a very, ano pa, down the line pa. Try muna natin, other than 6-2, paano tayo makakuha ng preliminary na cross-section? We must be wary of, again, C sub B sa pagkuha ng, so kung alam natin yung loading, may makukuha tayong C sub B, we have to be very mindful na kung ano yung target mo na capacity, kaila, kung titignan mo na siya sa mga table, i-divide mo siya by C sub B. So halimbawa, meron kang solve na C sub B. Tapos, meron kang M sub U right here. Diba? May na-solve ka ng factored na moment. Ito yung maximum na moment. Doon nangyari maximum moment, tapos meron kang C sub B. Ang hahanapin mo sa table na M sub N is actually M sub U over C sub B. Ganun mo siya hahanapin at this point because the following tables offer this part right here. So, sorry. Meron kang, okay. So, meron kang table 3-2 on which, ganito yung pagkaka-sort niya. Meron kang Z sub X, halimbawa selection by Z sub X, pero at the same time, meron ka na ring plastic moment na capacity agad. So meron ka ng plastic moment. So halimbawa granted na compact yung yung L sub B is less than L sub P. Ito na agad yung capacity na pwede mong makuha. Pero at the same time, tinutulungan din tayo kasi remember ang haba-haba ng formula particularly for L sub R. May lookup table na agad for L sub R. Granted na 50 KSI yung F sa buhay mo. So 50 KSI, so whether A992 steel or A572 grade 50 steel yung gamit sa cross-section mo. So meron nang in-offer sa'yo na L sub P at saka L sub R. So pwede mo nang magamit to to interpolate between the two values. And actually, meron pang isang mapapakinabangan, yung MRX dito. So dahil meron ka ng Pm and X is essentially equal to PMPX minus PMPX minus PMRX. Ayun, may nakita ko na yung nakatakip pala. So multiplied by L sub B minus L sub R divided by L sub P, L sub P pala to. L sub R minus L sub P. So, lahat ng kailangan mo na parameters para makuha yung inelastic FLB dito na sa table 3-2. Tapos, meron pang additional shortcut na ino-offer. Itong part na to is already termed as phi PF, itong part na to. So all you have to do is to get yung difference ng L sub B sa L sub P, then meron kang phi BF right there. Then yun yung ima-minus mo kay MPX para makuha yung capacity ng beam when expecting mo na inelastic lateral torsional packing. While at the same time, nandito na rin yung shear capacity ng bawat beam mo. Granted na, ito ay granted na walang tension field action. I believe baka next meeting na natin ito ma-discuss. And walang web crippling na nangyayari due to the shear. Tapos meron ka ring selection using IX. So ito I believe magagamit mo to sa combined axial and bending. So babalikan natin ito. So ang daming assistance na ino-offer si AISC for you para makakuha ng intelligent na guess. But remember na meron kang strong axis na bending, meron ka ring weak axis na bending. So meron kang selection by Z sub Y. So differentiate. So tatlong column. So anong mapapansin natin dito? Teka lang. Wala ng L sub B, wala ng L sub wala ng L sub P, wala ng L sub R, tapos wala ka na ring MRX, wala kang MRY. Bakit ganon? It's essentially because walang lateral torsional buckling na nangyayari along the weak axis. Hindi mangyayaring lateral torsional buckling if naka-orient ng ganito, then naka-ganyan siya. Because in the first place, itong dulo lang yung subjected under extreme compression to the point na walang buckling, or rather, hindi, kung mag-buckle man yan, hindi magkakos ng unnecessary na torsion. Rather, ang magiging governing na lang dito is FLB. Yung FLB dito, mag-buckle ng ganyan, magre-reduce ng konti yung effective na strength na kakayanin niya. Kaya ganito yung layout lang na selection by Z sub Y, tapos M and Y lang yung available natin na values. So ganun yung selection. So pag sinabi na yung bending moment is along the weak axis. So nandito yung bending moment mo, weak axis. So ito yung gagamitin natin, 3-4. Tapos similarly, pwede din yung selection using I sub Y. Then, on top of that, meron pa tayong table 3-10. So sa 3-10, gagawin na lang natin is alam na natin yung unbraced length. Halimbawa, so sinabi mo na 20, nagbigay ng example or sa design, sabi yung unbraced length mo is 20 feet. Tapos yung halimbawa MU mo is equals to 4,000 cubic foot. Tapos yung C sub B na na-compute mo based dun sa loading is around 1.1. 1.1. Wala palang dimension yan. So 1.1 siya. So ang tanong, paano mo gagamitin ito para makuha ano yung section na capable to? Siyempre, dahil may C sub B ka, ang gagawin mo muna is i-divide mo yung 4,000 cubic foot by yung C sub B, yung M sub U natin. So divided by 1.1, meron kang 3636. So banda siya dito. 3636. Tapos binigay na 20 feet. So it's between 18 and 22 right here. So we draw a vertical line dun sa 20 feet. We also draw a horizontal line dun sa 3636. So yung blue palagi pag pag LRFD. Yung green ay yung ASD. So kung saan siya nagsalubong dito, ang gagawin mo is maghahanap ka ng cross-section na directly above or dito sa first quadrant. Dito ka maghahanap ng ideal na cross-section. Hahanapin mo alin yung pinaka magaan. So ano yung mga candidate? Meron kang W40 by 294. Sorry. Ano lang tayo? Ano ito? W40 by 249. W36 by 262. 294. 370. 262. 331. 290. 257. Ang hahanapin natin, syempre, is yung lightest among doon. So, yung lightest is yung W40 by 249. So, ito yung lightest. Ito yung naka-jackpot sa ating selection process. So, ito, W40 by 249. Siya yung pinakamagaan among dun sa ini-scan natin along the first quadrant. And what does this indicate? So meron kang W40 by 249, Kapag merong kang gantong dot, this delineates yung essentially, ito yung L sub P natin. This delineates yung behavior niya na this is yielding alone. Tapos ito ay inelastic LTP. Ganun natin pwedeng gamitin si table 3-10 to make an intelligent guess. So, ano pa ang difference? Meron kang ganito. So, to highlight lang, so meron kang solid na dot. So, ito yung inelastic LTB. Ito yung fast yielding. Tapos dito, meron kang elastic LTB. So this hollow dot right here represents yung boundary between the inelastic LTB region to the elastic LTB na region. So mapapansin mo, straight line dito, kurbada na yung linya. Yun yung ini-indicate nito. So, ang parang this will able engineers to devise na ay, hindi ko gusto ng elastic na LTB na limit state. So, pwede kong malimit na, at ang acceptable sa akin is magsaselect ako ng procession na at least in elastic LTB yung governing failure mo. Kasi kadalasan, yun naman yung magbibigay sa atin ng pinaka magaan ng cross-section. Okay, kasi halimbawa, binigyan ka ng ganito, 18 cubic foot. Binigyan ka ng 8 feet na haba lang. So lahat to pwede. Kasi nakuha mo is W8/10, W8/13, and so on. Siyempre, kung sinelect mo si W8/10, okay, inelastic LTB pala yan. Gawin natin na 10 feet. So binago natin, i-revise natin ng konti. W20/12, W8/13, W8/15, W10/17, W8/18. So si W8/18, si W10/19, si W12/19, si W12/16. So si W12/16 ay inelastic FLB, LTB dito. Pero si W18/15 sakto nandun siya sa inelastic LTB. So medyo lusot pa siya. So ganun yung magiging criteria natin na pwede mong i-limit na kung anong limit state. So these dots will enable you to distinguish nasaang part na siya ng behavior na at this length inelastic LTB, at this length elastic LTB na siya. Then at the same time, again, para to assist you in getting yung C sub B, kailangan advantage na at least kaya nating mag-beam analysis ulit on which we have to derive yung shear at saka yung bending moment functions kasi doon natin i-identify nasan yung maximum shear, nasan yung maximum bending moment. This time, parang AISC is also offering you some assistance in defining ano ba yung function na yon. So for each of the simple beam loading, meron kang functions na available on which meron kang reaction forces. So eventually, kung ano yung mararanasan ng connections mo, designing yung connection details, nasaan yung maximum shear, saan nangyayaring maximum shear, tapos nasaan yung si maximum moment. And then at the same time, when we, halimbawa, nabigyan ka ng case on which may bracing ka dito, may bracing ka dito, may bracing ka dito. So, ito yung kailangan natin kunan. So, meron kang M-max dito. Tapos meron kang MA, tapos meron kang MB, meron kang MC right here. So, ito yung MA mo, ito yung MB mo, ito yung MC mo, and so on. So, pwede mong magamit yung mga functions na ino-offer. So, meron kang MX if X is less than A, halimbawa, tapos ito yung MX na una, tapos itong pangalawa is itong dito, from here to here, tapos ito is from here to there. So, yun yung ino-offer sa inyo. Then, ito, i-discuss ko na lang next meeting, yung available na shear stresses for, for flexural members. I believe, kailangan, parang may na-skip ako na part dito. Sige, ito. So, if you want to design naman members for shear, yung formula for I-shape members is simply this. Meron kang BN, we take note na yung under strength factor mo is still 0.9. So kung i-compare mo, dapat ay ganito. Lagi. So yung VN mo ay equal kay 0.6, yung ating yielding stress. Ito ay nanggaling sa energy criterion of Curie. So theoretical, parang kung recalling yung Flexure, so meron kang supposedly 0.58 F sub Y. Yun. Pero this time, yan, 0.6 Fy. Tapos, ang kinoconsider lang natin, yung area ng web. So, yung area ng web is H times T W. So, yung area ng web natin. Tapos, meron kang C sub V1. Ito ay depende kung meron kang additional na actions pang nangyayari. So, if hot rolled na on which yung limiting width to thickness ratio mo ay yung width to thickness ratio is less than this 2.24 E over F sub Y, well, it's safe to say na yung C sub V na yon is equals to 1. Pero if na-exceed niya yon, kailangan nating, alam mo, na-exceed ito in particular, yung 1.1 times K sub VE over F sub Y, kailangan natin i-compute yung C sub V1 natin. And medyo magiging particular na ito kasi yung web, so if we were to draw yung I na section, pwede kasi magkaroon ng web crippling right here. Para siyang umumbok. Kung titignan natin yung side view, yung itsura niya parang umumbok siya na ganito. And to prevent yung web crippling na yan, kadalasan naglalagay ng transverse na stiffeners. Parang sinasabi na mag-steady ka dyan, webs. So, mahalaga ngayon yung spacing ng transverse na stiffeners natin. Yung H is etong height, yung depth ng web natin. So, mahalaga na yung A over H squared para makuha yung K sub V para ma-revise yung C sub V1 in case na there's a potential na magkaroon ng web crippling. And ma-update ngayon yung ating V sub N. We'll discuss some examples in future lessons. Sorry. So questions, meron naman ata. Sir, yung unbraced po ba yung LB? Yung unbraced length, yung LB. So kung laterally braced throughout, yung LB mo ay equal to 0. So dahil infinitesimal ngayon yung strength, plastic yielding supposedly mag-govern unless kung chinek mo for flange local buckling, nag-fail siya, kailangan mong i-consider yung flange local buckling as your potential limit state. Any questions so far? So over the undas break, I'll try to post some examples, parang some sample solutions para pag-eksperimentuhan nyo. Pero so far, you deserve the break that you need. So syempre wala naman talagang pasok sa Friday. I'll see you face to face. If wala nang tanong, next meeting which is on November 6. So kita-kits tayo sa November 6 discussing some examples. Then babalikan natin a little bit yung theory, bakit gano'n yung naging formulations. So far, nire-introduce ko lang kayo dun sa code provisions. Wala ng questions?
Wala na.
Okay, kailan daw makukomplete yung score sa LE1? So to give you a context, kahapon lang nahanap ni Carlo kung saan ko nilagay yung LE1 nyo. So, tapos take note pala, dahil si Carlo rin yung isa sa checkers ng LE1, ng LE2, isa siya sa gumawa ng problem, ay naka-leave kasi siya hanggang November 8. So, a week after pa, marirelease yung problem 1 niya. Okay ba? Yes, I'll try to upload yung link for today. Tapos ayusin ko na yung notes. So, good luck sa ating lahat ha. So, hoping na kayanin natin. And so far, syempre, I deserve the rest that you need for today, and that will be all kung wala ng questions. Thank you for attending. So, at least naka-11 tayo, siyam tayong umattend ngayon. So, alam natin kung sino yung lalaban. Thank you, thank you.
Thank you,
Thank you
sir.
po, sir.
Thank you po, sir.